All right, how's it going today? Good. So, any questions up front? I'm doing well. It's sunny today. It's getting warm. It's like freezing this morning, and then it's going to be 50s this afternoon. So it's kind of weird. Back east is still getting hammered with snow. That's right. Should be like sort of happy. So, did anyone play with this this four-state system?
Yeah.
What did you find out about it?
Well, I found out the output. I tried to find out Q plot, but I couldn't.
Okay.
So I'm having a hard time with that.
Yeah.
Is it? It stays at 0 until 1 event period, and then from there it'll repeat alternate ones and zeros until two ones are entered.
Okay, so it stays at 0. So let's do it like this. So if you put in zeros, it's going to stay at 0. It's going to keep outputting zeros. And then you put in a 1, and it's still going to output a 0, but go to this state. And if you output another 1, it's going to output a 0, but go to this state, and then it's going to keep outputting 1s. And then if you put in a 0, it's going to output a 1, but come over here. And if you input another 0, it'll output a 1, but come back to your original state. Now you're back where you started.
So that you enter 1 0 1 0 1 0.
So 1 0 1 0 1 0. So 1 brings you over here and outputs a 0. 0 brings you over here and outputs a 0. Sorry, that's under there. And then a 1 outputs a 1 and brings you here. And a 1 outputs a 0 and brings you here. And a 1 outputs a 1 and stays here. And a 0 that's not quite right. I did. So let's do this. We're in state 0. You put in a 1, it outputs a 0 and brings you over here. You put in a 0, and it outputs a 0 and brings you to state 1 0. You input a 1, it outputs a 1 and brings you back here. You input a 0, it brings you a 0 and brings you back here. So now it's bouncing between these two states. Of the what? Mm-hmm. Okay, so this is another way to look at these, is try to figure out what the states do, right? And this is a key observation. If you're in state 1 1, your output's always going to be 1. If you're in state 0 1, your output is going to be 0. If you're in state 1 0, your output's going to be 1. If you're in 0 0, your output's going to be 0. So if you're in state S X Y, your next output is X. Oh, cool. Okay. So what's the second bit of the state have to do with anything?
Is it the bit before it?
Yeah, it's the bit before. So let's think about this. Suppose your input is a bunch of zeros except for a single one. Okay, these zeros are just going to output zeros and leave you here. When you input a 1, you're still going to output a 0, but you're going to come over here to state 0, 1. And now you're back to inputting zeros, so that's going to output a 0, but it brings you to state S1, 0. And now you input a 0, it outputs a 1, and brings you back to the beginning, and now you're just going to repeat. So what did it do to this 1 effectively? It shifted it. It delayed it 2 clock ticks. And if you think about that, that's what's happening down here. All of these 1s got shifted over 2 time steps. And these got shifted over 2 time steps. We did something wrong here. So this is a delay circuit. This takes your input and it outputs a delayed version of it. And it's delayed by 2 steps. So the other way to look at this is X is your previous bit and Y is your latest bit. So if you input a 1, you go to a state that ends with a 1. If you input a 0, you go to a state that ends with a 0. And the starting bit is the starting bit here, and the state number is the state that you saw 2 spots ago. So this is just kind of cobbled together to do this delay type action.
This is one of those things that if you stitch a bunch of them together, they all add up.
Yeah, yeah.
You can afford it.
So you can build computational engines out of state machines like this. It's not usually done, right? But it's potentially intriguing. And again, it's a finite set of states. It's a finite amount of hardware to build this, but it can process an indefinitely long string without problem. So state machines have been around for a long time and understood for a long time. But we don't usually deal directly with state. Well, we deal with state machines in hardware design. But in programming, in computer science, we tend to think of ways to implement algorithms with something other than present state input, next state output, right? And the classic model for computation that we deal with is a Turing machine. A Turing machine is still a state machine. It's basically described by a table which says present state input, next state output, plus some other things. But it's a particular style of state machine that lends itself very well to implementation in a practical system. So these things, computers, tablets, smartphones, all of this, they're Turing machines. Okay, they're all at some level equivalent to the system we're about to describe. And Turing machines, so who was Alan Turing? Mm-hmm.
He predicted the Enigma thing.
Yeah.
Yeah.
Yeah, he was a mathematician, and he was brought over to, can't pronounce it, Bletchley Park, one of those. It was a secret organization in the British government dedicated to trying to crack ciphers that the Germans were using. And he was brought in, and part of what he did in working on this problem was come up with this model of computation, this thing called a Turing machine that was eventually built into an actual physical machine and was used to help crack this German encryption system called Enigma, which was a really powerful encryption machine. You would type on it and encrypted text would come out the other side. And it had a series of dials that you could set to whatever combination you wanted, and depending on how those dials were set, you would get a different encryption. And each day they reset those dials to a different starting position, and so they had a totally new cipher. It was basically changing the password every day. And if you could crack this system within 24 hours, you had a chance of deciphering messages in real time. But combinatorially, the number of things you had to try, the number of operations you had to perform would take you, years or worse to just kind of brute force an attack on this. So coming up with a system, a machine that could actually do this was pretty revolutionary. There's a lot of folklore around Alan Turing. There's a really cool movie, The Imitation Game. There's a lot of novels that have been written, and we just passed Turing's 100th anniversary a few years ago. So there's a lot of popular press about him. I'll confess I have a hard time knowing exactly what's real and what's myth. I haven't done independent research on my own, but it's safe to say that he was one of the founders of modern computing. His ideas about Turing machines fed into a lot of the early work that was done with the original computer development in the 30s and 40s, leading to stored program computers, which is what we have today. Definitely an interesting character to investigate if you like biographies. So what is a Turing machine? It's a theoretical model of computation. It doesn't actually exist. You can make a mock-up of one. But it's a thought experiment, right, with the idea of how can we formalize this idea of implementing an algorithm with some sort of mechanical or other artificial system. And so we can envision the machine looking something like this. There's a tape, generally a magnetic tape, and it's infinitely long. That's the first nice little detail. So the tape's infinitely long. The tape is basically your memory. So a Turing machine has unlimited memory. And sitting on top of the tape is a read-write head. So how many people here have ever seen a reel-to-reel tape recorder? Or how many know about reel-to-reel tape recorders? How about cassette tapes? How about 8-track tapes? Okay. So, may as well pull up a picture just for fun. So reel-to-reel tape machines, they still exist. $1,200. That's used. Where'd my picture go, man? Give me a good picture. Plus $300 shipping. Why does it cost $300 to ship one of these things? They're really heavy. Yeah. But no, it's probably expensive to ship, right? These things are beasts. They're large mechanical systems. They have motors inside, and these motors very precisely control the movement of these two spindles. And you have a reel, plastic reel with magnetic tape wound around it. Okay, very thin, thousands of feet worth of tape, and the tape moves from side to side. Should be a good big image. Yeah, it's not bad. So tape moves from side to side, and it goes through a mechanism, and in that mechanism is a what's called a read-write head. It's something which can detect the magnetization of small dipoles embedded in this tape, and basically tell what the magnetic field strength is and what direction it's facing, and can also change that magnetization on the tape. So the tape's coated with some kind of compound, an oxide of some sort that can be magnetized in different ways. And you can use this to record typically voice and music and things like that, but also binary information, right? So this was the large storage system for early computers. So in a Turing machine, we have this fictitious tape with this read-write head, and we can write symbols onto the tape. So your alphabet can be whatever you decide for your problem. It might be 0 and 1 and a few letters. It might be the whole ASCII character set. It's up to you, okay? It depends what you're trying to define, but it's basically the vocabulary of your language. So you have a read-write head, and normally the tape is moving, but when we're doing this on paper and trying to work this out, we imagine instead that the head is moving. Okay, that's not physically practical, but it's a whole lot easier to draw a bunch of symbols and then just sort of move our pen around left and right. So when we talk about left, we're actually talking about effectively moving the head left, which means moving the tape to the right. Don't get bogged down in that. All right, so we have an infinite long tape. We have a read-write head, which can read a symbol underneath it on the tape, or it can write a symbol. And so we think of the tape as being broken into these discrete cells. Right, it's a discrete structures course, so we're still discrete. And you can also move the tape in one direction or another, okay, moving the head. You move it from one cell to another, so either left or right, and you can move it one spot at a time. All right, so what do we have? We have a symbol currently under the head. We have the ability to write a new symbol under the head, to move the head left or right. And we have a notion of state, okay, just like in a state machine. So the Turing machine is going to be a four-tuple. So S, I, F, and S0. So S equals the set of states. I is your alphabet. So the set of all your symbols. S0 is your initial state. And F maps from S cross I, so the set of all combinations of states and characters from your alphabet into this weird little thing, into a new state, a new symbol, and a direction in which to move, left or right. Okay, so that's the math version of it. What does this mean practically? Let's look at a state machine. So here's a state table. So state S0, if you have a 0 under the head, let's move to state S1, and let's write a 1, and let's move right. If you're in state S0 and you have a 1, let's move to S1, let's write a 0, and let's move right. If you're in state S0 and you have B, so B equals blank. So an empty space, and we sometimes assume the tape's initialized to all empty spaces. So we have a way to detect when there's nothing interesting on the tape. So if you're in state S0 and there's a blank, we'll change to S1. We'll write a 0, and we'll go to the right. If you're in state S1 and there's a 0, we'll go to S2, write a 1, and go left. If you're in state S1 and there's a 1, we'll stay in S1, we'll write a 0 and go to the right. And if we're in state S1 and there's a blank, we'll go to state S2, write a 0, and go to the left. I honestly don't remember what this does. But let's just explore this. Okay, this is the analysis portion. We've got a state machine, okay, a Turing machine. This is the state transition table. We want to see what it does. So let's imagine that our tape has a bunch of blanks, and then a 0, 0, 1, 1, and then a bunch of blanks. And S0 is going to be our initial state. So you got to know what state you're starting in. And you've also got to know where the tape is sitting initially. So let's suppose that we're sitting right here on top of the 0. So to understand what this system does, we simply look at the state table and apply whatever change is dictated by the table. So we have a set of 6 things in our state table. At most, one of these is going to apply. If none of these apply, the system halts. It's done. All right, so we're sitting in state S0. We know that because that's our initial state. So our current state is S0. And there's a 0 sitting under our head. So is there anything in our state table that says our current state is S0 and there's a 0 under the read-write head? That's this right here. Okay, so this is current state, symbol under the tape. Next state, symbol we should write on the tape, and then how we should move. Okay, so this is the only rule that applies. We're in S0 and there's a 0. So this says we should move to state S1, and we should write a 1 underneath the head. So this should become a 1. And then we should move to the right. So now we should be in this situation. And now we just keep doing this over and over and over again. So we're in state S1 and there's a 0 under the head. Is there a rule for that condition? Yes. It's this rule right here. You're in S1 and there's a 0. It says we should change to state S2. We should write a 1 under the head. And we should move to the left. So we come back to sitting right here. And now we're in state S2 and there's a 1 underneath us. Is there a rule for that condition? What did you say? No. There's no rule for what to do in state S2 regardless of the input. So now the system halts. And it's done. So what did this do? It changed 2 zeros to 2 1s. Not terribly interesting. But that's how this machine works. Okay, suppose our input looked like this. So we're sitting over here, and our initial state is S0. And this is what's on our tape. So our current state is S0. We have a 1 sitting underneath the head. So what should we do? We should write that as a 0. What should our new state be? S1, good. And which way do we move? We move right. So we were using this rule. State S0 with a 1, change to S1, write a 0, move to the right. Okay, so now, do any of these rules apply? Okay, which one? So we're in state S1, there's a 0. So write a 1, move to S2, and go to the left. So we're in S2, there's a 0. Do we have a state for that? Nope, system halts, we're done. So with 2 zeros, it changed the input to 1, 1. With a 1, 0, it changed the input to 0, 1.
Looks like it
Looks like it toggles the bits unless it's blank, in which case it writes a 0.
There's that one case where S1 goes right.
Oh, I don't know. Let's find out. So suppose our tape contains 1, 1, blank, 0, 1, and then blanks on the left and the right. And we're sitting over here. And our initial state is S0. All right, we're in S0 and there's a 1. So we want to write a 0. We want to change to S1 and we want to move to the right. Now we're in S1 and there's a 1. This says write a 0, stay in S1 and move to the right. Now we're in S1 and there's a blank. What do we do? Put a 0, move to the left, and go to S2. And there's no state with S2, so it halts. So a 1, 1 changes to a 0, 0, but also writes a 0 to the right if there's a blank. So this is some kind of weird machine. It doesn't really have an obvious purpose. Yeah. All right, so let's try another one. You got the idea of the mechanics, right? Okay, so let's start looking at some more arguably useful. So what could this possibly be doing? It's only got 3 rules. What does it do if there's a 0 under the read-write head? It gives you a 0, it moves to the right. And it stays in the current state. What if there's a 1 under the read-write head? Gives you a 1, just moves to the right, and it stays in the current state. So it moves from left to right until you get to a blank. And what does it do when you get to a blank? It backs up and it quits. So this is possibly useful. So if this is what our string looks like, and we're originally pointing anywhere inside this number, this will basically move all the way over to the blank and then back up 1 spot. It won't change anything on the tape. It basically moves you to the least significant bit of this number. Well, that's potentially useful, right? And in this case, it halts because then it goes to state S2. But suppose we add some more states to this. Now it's just toggling all the bits. If it sees a 0, it's going to write a 1, move left. If it sees a 1, it's going to write a 0 and move left. And so it keeps moving to the left while it's, while it's toggling the bits until it gets to a place where there's a blank. And when it sees that blank, it leaves the blank intact, but it moves to the right. So now it's pointing to the most significant bit, but it's complemented your number. So this gives you a 1's complement of a binary number. And if you start in state S0, you can begin anywhere over that number, move over to the beginning of it, and then move across it, toggle all the bits. So that's potentially useful. All right, let me change these states. Let's put in some different states for S2. And the state names are irrelevant, right? They're just names. We could call them ABC. We could call them S5, 10, 15. It doesn't matter. They're just names of states, right? So I'm not doing S2 because it's magic. It just came out of my head. So let's see if we can do this. I always have to. Give me 1 second. All right. Let's see. If I did this right. So this is a little different from what we had before. So what's the action here? So this still moves you over to the least significant bit. If that bit is a 0, it's going to change it to a 1. It complements until it hits the first 1. And the first time it hits a 1, it will complement that. But then it goes to S3. And what's happening in S3? It's just writing the same thing that it's reading until it gets to the blank, and then it backs up 1. So this takes a number like this.
That adds 1.
Yeah. It takes a number like this, it complements it, up to and including the first 1, and then it leaves everything else the same. That's not what I wanted it to do. Trying to do a 2's complement. I did it backwards. I knew I'd get it wrong. Yeah.
I guess it was just 1 and 0.
I kept the first half with the S0, and then I went into, so with S0, it'll go all the way to the right until it's a blank,
Mm-hmm.
and then it'll back up 1, and then it'll go into an S1 state. And then if it's 0, it'll back up until it's a 1.
Mm-hmm.
If it's 1, then it'll change its state to an S2, and then that's when it'll start flipping bits.
Right, right. Okay, good. What he said. So yeah, move over to the right. If you have a 0, leave a 0. If you have a 1, leave a 1, but then go into state S3, and state S3 complements all your bits. So that's the shortcut we learn in 250, or some of us learn, apparently I don't, for finding 2's complement. Right? Start with the least significant bit, leave everything intact up to and including the first 1, and then toggle all the remaining bits. And that's the same thing as complementing everything and adding 1. So there's the adding 1. So this is a Turing machine that if you have a binary number on a string and you start anywhere over the string, it will replace that number with its 2's complement. All right, so you could use this as a preliminary step for doing subtraction. If you had a machine that could add 2 numbers, well, you could take the second number, replace it with its 2's complement, and then go ahead and add them together.
Is there anything in the Turing machine that describes like some kind of other output?
Describes what?
Like if you wanted to say, if there was a printer hooked up to it, you could say, and then when you get to the 0 at S4, print my taxes out.
Okay. Not in a pure Turing machine, but we could. So how do we do this on a regular computer? We do what's called memory mapping. So we have memory locations where you store your 1s and 0s, but some of those locations aren't actually memory locations. If I write a number into this particular address in my memory, instead of going into memory, it goes to my printer. Right? So that's one way that we hook devices up to regular computers, and we could do something like that on here, except our wires would get twisted up in the reel. But yeah, similar idea. But a pure Turing machine, the whole output system is just the tape. But yeah, we could embellish it.
Yeah, that's not like an unreasonable thing. If you could always, if it was an audio machine, you could just take the tape.
Yeah, yeah,
That would figure it out.
yeah. Or you could put a scanner on top of the Raspberry Pi to like optically decode what's written on there. People have made Turing machine models. They're kind of fun to see. And it's not a bad thing to try to simulate because it's a very simple system. So here's my favorite Turing machine simulator. So this is online, and it lets you load in a program over here and simulate it and see what it does. So here's the head moving back and forth, and here's what's written on the tape, and it's got different sample codes. So let's look at binary addition. So we'll make our own input. So what, go ahead.
I was going to say this doesn't, oh, but it isn't. Okay, no, it isn't.
Yeah. So what number should we add? Someone give me your favorite number, as long as it's not big. 17. And 7? Okay. Let's do 17 and 7, because I can convert those to binary. So there's 17, and there's 7. And we need to load that in. So that's what's on our tape originally. And this is a Turing machine program for addition. So there's some embellishments here. There's some wildcard symbols that you can use to say match anything. But otherwise it's pretty straight Turing machine. So, and it's got comments, right? Because comments are good, right? We know that. And it starts in state 0, so it's just going to go ahead and execute. So there's not a blank under the tape, so it's going to start off with this instruction. And we can single step this and see what it does. And it's moving over to the right until it gets to the first thing before a blank. And then it's going to eat those symbols, but based on the symbol that it eats, it goes into a different state to effectively remember what that symbol was. It uses some placeholders like X and Y, I believe. And it halts finally, and there's our answer, 24, and that's 17 plus 7. So that's not too bad. And you can just run this thing and watch what it does. And it took 99 steps, so 99 clock cycles.
So with an actual magnetic tape, would it run that fast, or would it run faster or something?
Magnetic tape can really fly. It's pretty impressive how some of the more advanced machines before it kind of went out of vogue. It can move really fast, definitely faster than this. And the reels would spin, but they used a pneumatic system to basically suck the tape into a little holding area. And by adjusting the vacuum, they could get very minute movements of the tape from one side to another without having to mechanically tweak it. And yeah, it was pretty cool. And of course, every now and then something goes wrong and it just eats your tape, and you get this wrinkled mass of work that you have to fish out of the mechanism. And yeah, it's good stuff. All right, so this is a multiplication program. So it's a little longer. It's 119 states with comments. And it takes two numbers and multiplies them. So let's go back to our numbers. So 17 times 7. And what is 17 times 7? I have no idea. What is it? Oh, okay. 109? Or 119? Well, it doesn't matter because we want it in binary anyway. So it should come out to be like this. So 127 minus 16, minus 8. So 119, I think. All right, but that's the number we're after. So let's go ahead and run this thing on the multiplication program and see what it does. And multiplication is a little harder than... Did I actually load that tape? Let's try that. Multiplication is a little harder than addition. And we can say run at full speed. And you can see the step count up there. So 813 steps, and there's our product, 1110111. So that's 119. Cool. Awesome. I don't think they have division on here, but they do have a primality tester, which is cool. So what's a good prime number to test? All right, we'll try 7 for small, and then we'll try 23. So this is a total of 215 states. And let's see what it does. So it's got to do division along with some other things. So 1,500 steps. And it's prime, 2,600 steps later. So let's try 23. And we'll just let that chug. So Turing machines are useful as theoretical objects, right? They're useful to study questions about computation. They're not entirely practical. If you wanted to test prime numbers, you probably wouldn't write a Turing machine program to do that, but you could. And anything that you can do with an Intel processor, you can do with a Turing machine. And the terminology usually goes in the other direction. People will say that an Intel processor is Turing complete, which means an Intel processor can do anything that a Turing machine can do. And that's really the benchmark for a programming language or a computing system is, can it do everything that a Turing machine can do? And if it can, then we say it's Turing complete, and it's considered to be, you know, as good as anything else. But this is obviously in many ways, inefficient way to do computation. 12,000 steps later. But you can.
How do you crack the Germans'
It wasn't done with a Turing machine. It was done with something much more down to earth. But it was, and I don't know when the Turing machine itself came along in that development of the original system that cracked it. But it was a model of computation that Alan Turing and others presumably were thinking about. But the tape basically translates into our memory in a computer, right? And what does our computer really do? It reads information from the memory, and it writes information to memory. And it has a notion of state, right? That's the program counter / the instruction that you're executing. And it's a fairly direct map, except we have finite length tapes in our computers. Not a huge impediment, it turns out. But we're working on a 5-bit number, and it clearly needs more places on the tape than just those 5 bits. Right? It needs places to store temporary variables effectively that it's using to work its way through this. I don't remember how many steps this takes, but we got 2 minutes left. So there's some homework questions related to Turing machines, asking you to look at Turing machine programs and describe what they do to certain input strings. Hey, it's prime, good deal. All right, 28,000 steps. 2 is prime. Oh, something that's not prime? Okay, let's do 4. That shouldn't take too long. I think it just says is not prime. I mean, we could crack the code and see. But somewhere in here is the output part that's actually writing that. Not a prime. Duh. Yeah. So there's some homework problems that let you work on this. The synthesis side, right, is clearly a lot harder, but we can do things like adding 1 to a number. We can do things like adding 2 numbers together. And the more you do these, the more it becomes sort of clear how to piece these things together. Kind of like writing a state diagram for a system, kind of like writing a phrase structure grammar to identify a language. It's not something you're going to be responsible for. I'm not going to have you code a complex Turing machine on an exam, right? But I might have you do some analysis, show what this machine does to this input string, that kind of thing, just to test understanding of the mechanics. But as I said, they're mostly useful as a theoretical model of computation, and this is what we're going to start with tomorrow, is we're going to talk about variations on a Turing machine, and this is going to take us into one of the most fascinating areas of computer science, the question of NP completeness. And this is the stuff of folklore and standing $1 million prizes and all kinds of good stuff. So we'll talk about that tomorrow.